There you go.
Okay, so you guys have probably seen the new Architects Forum page. It looks different. It's now the same style as the rest of the Lithium forums because of reasons. So the biggest difference is that, well, first of all, it might be harder to find, but if you can find this page, you're mostly there. The second part of it is you need to click on group options and to subscribe. If you don't do this, you won't get emails about things that are posted here if you want to follow it. So your previous subscriptions are not carried over. So if you previously followed the Architects Forum page, you're not anymore, even though it might be confusing. So if you go to group options, subscribe, it will fix that if you want to follow this.
All right, let me show you how to find it. So if you go to ni.com/groups, that still works, and they say that it's going to work forever. And it basically directs you to the new community. Mm-hmm. And then from there, you can do the search. Just search for LabVIEW Architects Forum, and it's like the top hit if you do it that way. So if you search here.
This morning, I was doing LabVIEW Architects Forum.
And you found it?
Top 5.
There you go. So I don't know where is it. Yeah, I guess it didn't really. Oh, there it is. See?
Yeah.
Hidden there. Yeah.
So, and there's a way to find it in the left panel as well.
Yeah.
So, yeah.
I will also say is, because I've been having these problems as well with a lot of my groups not being subscribed anymore, in a number of cases, I only have unsubscribed. So the system thought I was already subscribed, but I wasn't getting any of the notifications.
Yeah. You have to unsubscribe and subscribe again. Yes. Yeah. Yes. So this is totally out of our control. The other thing I noticed is if the window is resized, it doesn't look as nice. And we lost the differentiation between questions and discussions or documents, which the documents made it easy to find the content for each meeting. I'm trying to see if NI can help us to get that back. So in the meantime, I know who's from NI? Probably everyone, right?
Do I count?
Yeah. So you guys got an invite, right? Internal invite. We did get the external. I think I sent it to you, Aaron. That was sent to Central Texas people. But we definitely lost audience. I was expecting that this was going to be a thin group. So, pass the word around about going to the page. And I'm going to need volunteers for the next session for presenters or topics that you want to see. Otherwise, it's like Damien and Aaron that they were by default the other two that were.
Remind me, when's our next meeting date?
Thank you, that makes me feel so good.
Oh, it's at the top.
Especially since mine's been postponed for 3 years.
Yeah, scroll around. Yeah.
I just stopped sharing, but yeah.
It's June 27th.
June 27th is our next meeting. I'm going to post to you.
So, yeah, I mean, I just said that because Damien was complaining that, lesson learned, I need to show up to every meeting, otherwise I'm going to get volunteered to present. So, anyhow, all right, Aaron, take it away.
Okay.
You should get a joining notification.
Yep, give me one. Let's get this hooked up. There we go.
Can you look the lights?
Okay.
Okay.
Taking myself off mute. So was I hearing myself on the back computer there?
I think you're hearing yourself on your own computer.
Yeah, unmute your mic.
Are we on the phone?
Yeah, that's
okay. So is that better then? Okay, so presentation I have today is one I had a hard time coming up with a good name for. The reason being is I'm going to talk about how I implemented a time-weighted average in LabVIEW FPGA. This was really my first LabVIEW FPGA project. This was a project I did about 4 years ago, shortly after I became an independent freelancer. And I presented about 3 years ago on the many lessons learned from that project and many of the things that went wrong. But one of the things that I had wanted to do as part of that project, but did not succeed during the project time, was to get this time-weighted average down from the RT portion into the FPGA. And there were a number of challenges, including the fact that the big one was that I was operating on an array of data which could be of variable length in size. And so obviously FPGA does not allow dynamic array sizes. And so years later, I went back to try and get this working as I gained more knowledge. So the background was this was a LabVIEW RT FPGA project that had a controller plus an EtherCAT expansion chassis, and the company wanted multiple types of scaling and smoothing of the signals. They provided me the LabVIEW reference code for weighted smoothing. It had a reset option. It had you were able to specify the damping time, the refresh rate of the signal, and depending upon that damping time and the refresh rate, it would grow or shrink the array of data that you were averaging. In the original LabVIEW basics, as I still call it, or the LabVIEW cores, we see about doing the simple 2 or 3 element weighting where all elements are created equal. What this code does is it weights older elements less, and the more recent elements have a greater weight to them. So you're not just dividing everything by 2 or dividing everything by 3. The older in time, the less it matters. But it still gives you a nice smoothing effect. So the key features there are weighted average, so newer samples count more, and it's a dynamic weighting based on the current buffer size or the max buffer size, and whenever we reset it, it starts the buffer size at 1. And so again, if we go back to like the LabVIEW cores, well, we usually leave those shift registers uninitialized, so you get some zeros in there. And so, if you start off at a temperature of 75, but you've got 2 elements of 0 in there, it really doesn't give you quite the same effect. So for trying to get this into the FPGA, especially when at the time there wasn't a lot of the better documentation that I'll refer to later on, but you need to do fixed array sizes, or at least you need to fake dynamic array sizes using fixed array sizes. And I also ran into problems in that you can't easily do too many operations without starting to get into timing violations in your compilation. So one of my first attempts at fixed size was this little monstrosity where I assumed it was going to be 10 elements. I pre-calculated my weighting factors, and it won't compile because of how many multiplies there were in it, even though they could all be parallelized. It didn't have a reset. It didn't have dynamic sizing. It couldn't get it done. I tried another option, which still won't compile, where I would just loop through and do the weighting on the first element, second element, third element, fourth element, and it would still give me timing violations, even though this module 1AI0 node was a module that had an 832 millisecond update rate, which to me meant you could just chain cascade a whole bunch of operations since they're relatively fast. The compiler won't handle it. Now again, I don't know if the current compilers will handle it any better. We are talking the LabVIEW 2011-2012 time frame is when I was trying to do this. Now I'm sure someone will be looking at that and saying, "Hey, you've got the unassigned tunnel. Of course, it's not going to compile." I didn't save all of my broken attempts. I would try one thing, compile it, try something else, and I finally just threw up my hands in disgust. So this is me recreating some of the stuff I tried years later, and I was just recreating enough for the demonstration. So later on, I chose to revisit the problem after acting as a team member on a project with custom FPGA communication code where someone else had written this code that I then had to learn, fix an error or two, and the code had an FPGA embedded state machine. and in order to do its communication. And a single cycle loop at 25 nanoseconds could actually allow a lot of state transitions compared to my 832 millisecond sample time. So could I, instead of trying to parallelize it the way I was doing, I had the thought of, could I get this time-weighted averaging by doing a state machine and implementing that in the FPGA? So I decided a couple years later, let's try again. So I decided to make some assumptions. First, that any individual channel could have a history of 20 elements, and I was going to start with a single channel implementation. If I could get that working, then we could go to multiple channels and see how well it scaled. So I decided to break down the pieces. The first thing is the damping time. The second piece is our data storage. Our third piece is our weighting factors. Our fourth is our weighting calculation, and then we have our accumulator. Most of the, quite a few of these functions will not work as you see them in this code in FPGA. The for loops aren't going to execute because they can be dynamic array sizes. There's definitely no equivalent of some array elements in FPGA. And so I had to break these down and figure out, is there a way I can implement these? So I started with damping time, and an interesting thing with the damping time calculation is the round towards infinity works on some FPGA targets and not on others. It's supported on some and not others, is what I found out. But the nice thing is this particular setting is a setting that's not going to change very often. This is a configuration setting of telling me how big my array size is going to be. So I said, do this as a host side item since it's a configuration change. And I said, okay, don't worry about this. Now this next piece is creating our weighting array. Well, for a given array size, the weighted array elements are always going to be the same thing. So if I had an array size of 2, my first element is 0.6667, it's 2/3, and my second element is weighted as 1/3. If I had an array size of 5, I have one that's 1/3, one that's 0.267, one that's a fifth, et cetera, et cetera. This calculation is never going to change. If I have 5 elements, I'm always going to have that weighting. So what I can do is I can pre-calculate this. And so I can create support for up to 20 memory locations, and I can store this as an initialized memory space in my FPGA and just store it either as a large array or as a memory block. And I started, because I wasn't as familiar with memory blocks, you'll see the first set of codes that I do will have this just as a large array of singles before I move into putting it in memory blocks. And you'll see some things along that way. And also, when you create memory blocks and when you create memory blocks, you can have an initializer to pre-initialize the values. And so here's the preview of what my data array is going to look like in that memory storage because I pre-initialize and then I read only from it. Now then I went about creating my state machine. So I have an idle state, I don't have any data, I don't have new data. I have an acquired data state, so my A to D just gave me a new set of values. I have to weight the data. And what I did was, after because it's now a state machine, I don't weight all the elements. I iterate through and weight an element, put it in an accumulator, check, have I weighted all of my elements? If yes, I go to my accumulator and finish and write my data out. But if I haven't, I go back and weight the next element, weight the next element, weight the next element. And so I created a little cluster to contain my information that I needed to preserve from loop to loop. I created my weighting array, and I created a memory array at the top that had 20 elements, that was pre-initialized for 20 elements. So I started with my idle, and here I could change my weighting size. In the idle, I check for changes to weighting size. I added the sequence structure in here to make it easier to put a breakpoint before I started doing anything to help with debugging simulated I/O. That's all that flat sequence structure is there for. It has no purpose other than to allow me to put the breakpoint before it for better probing. In my acquire data, what I did was I added a FIFO to decouple myself from my analog input loop. I place new data. When I get a new element, I place the new element into my circular buffer. I'm using this 20 array element as the circular buffer, and I calculate my data pointers. And hey, if my data pointer is at the last element, the next time around it's going to be the first element. Just, you know, standard circular buffer. I calculate my data pointers and I calculate my weighting size right here. So once I've acquired the data, I start going into weight. I go into my weight. And so I look at my counter, I increment it, is my current weighting greater or equal to determine whether I'm writing the data or do I need to iterate through my next element. Same thing, I have my last data pointer, my counter, and I'm pulling out what was my previous element, what was the element before that, as I iterate through. If I had 5 elements and, you know, my current position in my circular buffer is 10, I need to weight number 10, I need to weight number 9, I need to weight number 8, etc. And I have my current weighting size, which then calculates into an offset in that large array. Because if I have 5 elements, I built the array to handle 1 element, which has my 0th element. If my data array had 2 elements, I've got the next 2 elements, etc. So I need to know where I'm looking for in that weighting array. And so I have the calculation there. So then when I'm done, I take my accumulator that I was busy adding data into, and in this case, I'm passing it out to a front panel element. And so the nice thing is this worked. So this problem that I had never gotten working several years earlier, now I've got a working solution for it, at least for a single channel. And so when I actually compile this, I see about 7% of my slice registers and 12% of my slice LUTs being used. But what happens if I try and scale this to multiple channels? Well, one way of doing that was to change my data array from 20 elements to 160 elements. That would have theoretically, and do a little bit with my other pointers. And now all of a sudden, after I change a couple of those to arrays so I can track each channel individually, so I have 8 accumulators instead of 1, stuff like that, as well as adding a current channel, because just changing that, it's really that 20 element array to a 160 element array, took my utilization up to 40%, almost 40% of my slice registers and 80% of my lookup tables. That's not very scalable, especially when I have a lot more than 8 channels in the system. So what about starting to, instead of using shift registers on array, what if I start using memory for both my weighting array and my data? Well, shifting over to using memory, I dropped for 8 channels back down to just barely more than I had used for 1 channel.
So you're using memory space circular buffer?
So I'm using memory space both for my circular buffer and for that weighting lookup table. And so that got me a much more scalable solution. So then if I took that same thing and put it 16 channels and even up to 64 channels, at 64 channels I was using 30% slice registers and about 30% of my slice LUTs. That was a heck of a lot more scalable, and we see I'm only using, from there I went from 5% of block RAMs to 17.5% of the block RAMs. Now this was on a 9074, which was one of the low-end controllers with one of the low-end FPGA. So this wasn't a very big FPGA to begin with. Now, one thing I am going to point out is these numbers, I did not scale my I/O reads. So right now, I still have 1 channel reading into my buffer, even though I'm assuming that I can have up to 64 channels. And I'll show the numbers of when I actually add looking at 8 different I/O modules and putting all of the numbers in later on. But the key here is my state machine scalable? And the answer is, yeah, it's pretty scalable by switching off to memory. So what about performance? You know, I said some of my channels were 832 millisecond update rates, which is quite slow. relatively speaking, versus the FPGA being capable of 25 nanoseconds if you're using a single cycle timed loop. But how do I actually measure that? And, well, I could start putting timers in to see how long it took, but that could possibly vary a little bit compilation to compilation since I'm not using a single cycle timed loop. So I started experimenting, how do I make this code into a single cycle timed loop, and promptly learned some new things. You can't use the single data type inside a single cycle timed loop. The multiplication and addition functions that I was using don't work. So solution there is we can change this to the FXP, or the fixed point data type. And here I switched all my memory registers over, but ran into some other problems with my fixed point settings. My weighting array can be a relatively small value all the way up to 1.0 as my weighting factor. Well, my data from my I/O modules was the 0 to 21 milliamp modules, so my data could only be plus or minus 0.25, and all of a sudden my calculations are off because of the difference in the two how the two different floating points were set up. So then I have to make sure that I match for the weighting array and everything else to allow it to properly multiply and properly represent the value. So that got me partway into getting this to a single cycle timed loop. And I also learned that you need to use feedback nodes when using memory registers with this. And that's in documentation that I read later on, but I found out that, again, at least with older versions of LabVIEW, I haven't checked if this is still the case, you'll generate an error when you try and compile and you don't have the feedback nodes if it's a memory read.
Because it has to have the address first.
Because it has to have the address.
To give you the data.
But if it's a memory write, it will try to compile and it will fail the timing. And so instead of immediately erroring out when you're doing your intermediate file, so you've maybe wasted 30 seconds or a minute or two, instead you wait 10, 15, 20 minutes. As I built this, it generally took about 10 minutes to compile, but you're waiting about 10 to 15 minutes and you're getting, we can't compile it to hit the 25 nanosecond limit, we're getting 25.7, 25.8, and it's because it didn't have feedback nodes on the writes. But that took a while to track down.
You had more hair before you started this.
Yes.
It's actually not true of all FPGA stuff.
Okay, so it's not true of all FPGAs. Well, it's true of the FPGA I was compiling this for.
Yeah,
so,
you said older and
so I appreciate the additional information. So in doing this, we get our 64-channel utilization. We're using more block RAMs here, but still only about 20% of my FPGA. So there's other considerations. The particular analog module could operate in a high-resolution mode or a high-speed mode. For some of my channels, I needed high-speed mode. For some of them, I needed high-resolution mode. So what happens if we have loops of different rates? In the previous code, we assumed I'm always putting the data in order. I'm always getting channel 0, 1, 2, 3. What if I'm not? Also, how would I force the modules when I've got 3 or 4 different modules to all put the data into the buffer in the correct order without doing lots and lots of coding? What if 2 modules had different data rates, and how do I reset on a per channel basis? So what I did here was I changed my FIFO. The FIFO was plus or minus 421, which was great for my 0 to 21 milliamp signal. What I did was I added a plus 6 data block that gave me my channel number. And so by merging the data with the channel number, now I can put the data into the queue telling me what channel number it is, along with the data. So now it doesn't matter what order it's going in. It doesn't matter what, if I have a higher speed module and a lower speed module, because I know every element in the FIFO has its channel information in it. And if I wanted, I could get cute and creative and put in reset throw in a reset bit if I wanted to. And so I can use the function here to merge these two and then extract them out afterwards.
What is that function?
I'm forgetting the name of it.
High throughput.
High throughput. Thank you. Addition and.
You can do the same thing with two Boolean array and next.
Okay.
Because you're not actually, you're just putting those blocks together, right?
Yeah, I'm effectively putting the blocks together, and I was trying to get it so there's actually a couple of wasted bits in the middle the way I'm doing it.
Yeah.
But rotating the numbers was just being a little bit of a headache, so I said I'll waste a little bit of the memory to make it easier.
In Veristan, the way to do it is two Boolean array, and then for the FPGA interface, and you actually index that up and fill it back into its own fixed point number, and then
Okay.
cast it. And that's the clearest way I found it.
Well, this worked This worked pretty well for me. I hadn't considered that, but obviously, as you said, it works, and it would be a fairly clean way of doing it. And so, with my revised state machine, here's my idle. I have a Boolean that is apply new max weight. If true, I write it into the memory space for my max weight, my maximum weighting for the specific channel, and the maximum weighting size. I had a current, and I had the current in. Because the current could always be less than the maximum. So I have what is supposed to be my max. I had created what is supposed to be my maximum and how many data elements do I have currently. My acquire, I have my DQ element. I extract my channel, and I go to my next step being retrieve memory pointers. I extract the channel, put it into the current channel cluster element, and I say this is my first cycle. Then I retrieve my memory pointers. Now, again, we talked about that when we go to single cycle timed loop, we have to have the feedback nodes because our reading from our memory takes 2 iterations. And so what I do is, you'll see that I have, if this first cycle is true, or regardless of whether it's true or not, I invert it, and I come back to this same state a second time to get the real data. My first data is garbage, so I go through this state twice, and I can't do it as 2 separate states in my state machine because then the feedback nodes are irrelevant. And so what I do is I just hit this one twice and only care about the last set of data. Same thing with when I store the raw data. I do I get my data pointer. I do my lookups. I have a little lookup table there. The little the channel data address sub-VI is another case statement that gives me my lookup pointers. Then in my weighting data, I do the same thing where I iterate through however many elements. And again, I do if first cycle is true, do nothing, the data is invalid. Now in this case, the last state we saw, I went through twice, and only the second set of data is valid. This one I might go through 2 times, I might go through 21 times if I have 20 elements, but basically I don't care about my first data. I don't care about my data the first time, but the second time through, when I'm moving the pointers, well, I'm going to get the data in the third state, in the third iteration. So if I needed 20 elements, I would have to execute 21 times. I don't have to execute 40 times.
Oh, of course.
So then finally, I write the data off to, in this case, I moved it to memory location as well. So the final solution, I did break up some states to multiple states to allow the use in state control machine. And this had me, I was able to say, assuming a channel has the maximum 20 samples, an analysis will take 27 iterations through the state machine, which is going to be 675 nanoseconds. I know what my maximum time will always be now. So if I have a 64 channel unit, I know I can handle on average 1.4 mega samples per second across all 64 channels, which is 23 kilohertz per channel, if all of them are the same rate. But if I have a couple of low-speed ones and a couple of high-speed ones, I can have a couple of these going, at 5, even 10 megahertz, and a couple of these down in the kilohertz range. So now I've been able to revisit this, go to a 64-channel solution, and solve my problem that I hadn't been able to solve for the project initially. And so I did say that I was sort of fudging my numbers a little bit at the beginning, where when I went from 1 to 8 channels, I didn't actually read all 8 channels. I was just putting the same one in the queue multiple times. If I look at adding those channels back in now, we do go from our 30% utilization to about 40% utilization. So adding all the extra I/O module reads does affect my timing, or does affect my utilization, which I expect it to, but in terms of trying to figure out how well this state machine can work in the space allocated, I have the numbers both ways, and we saw that I could get it to grow to 64 channels with very little effort after I had started using memory instead of data arrays and shift registers.
Yeah, your usage rate doesn't grow as rapidly as channels.
Yeah.
Which is just where you want to be.
Exactly. So, conclusion, by reimagining the problem, not as a trying to parallelize it, even though normally when you think about FPGAs, you think about a lot of parallel operations.
Pipeline.
You pipeline it.
Yeah.
Which, had I known about at the time, and unfortunately a lot of the trading documentation that exists now didn't exist then, I might have taken a different approach.
You haven't taken the FPGA course, right? It was all
It was primarily self-taught, and there's a document that I'll be referring to a little later in my slide that did not exist had not been released at that time, that would have made things a lot better for me.
Yeah, on the LabVIEW training, they can go into quite a length on trying to explain, because pipelining is not something that's natural.
Right.
So there's actually some slides in that training that guide you through going from shift registers to feedback nodes to them doing the pipelining.
Okay.
So I recommend if anybody's going to be working on FPGA, definitely that course.
Yeah.
And I think you can access it online. You have the other.
Yeah, the older one.
The older version.
Yeah, the 2014 version. I don't think we've pushed it. The embedded course. Yeah, we haven't pushed the embedded, but the old, just pure FPGA training.
But also from a regular LabVIEW perspective, when you create this as a VI, and you might set this as a cloned VI for 64 channels, so each one has its own shift register, its own memory space.
Hey, you're not gonna
That doesn't work when you're going into the FPGA either. So, well, I mean, it can work going into the FPGA, because there were certain cloned things that I did for like watchdogs, enabling my outputs, stuff like that you clone and put dozens of in parallel. But for something like this, it doesn't work very well. So by going into a state machine type architecture, which does have pipelining, this allowed expansion to multiple channels in a way in which the FPGA fabric utilization was minimized. Now, if I found that for whatever reason I needed, X number of channels at 10 megasamples, I could actually I have the room this time around to actually put 2 of those engines in if I needed it to have higher speed for all of my channels. And it won't double my fabric, because at least the weighting array could be still a single weighting array. And this allowed me to operate on a variable number of data elements that could be changed in runtime, whereas at the beginning I'm like, I was just trying to get a fixed array of 10 elements working, and I never did, let alone being able to effectively, in theory, dynamically resize my array. Now, right now, I'm effectively resizing the array by using the circular buffers and operating on a variable number of the previous data elements. So it's still not truly a dynamic array size, it's a fixed array size, but you're dynamically working over the number of elements effectively giving you the same equivalent as the dynamic array.
On a dynamic array, but it plays one on your FPGA. There you go.
Exactly. So some of the other things that I didn't implement that could be done, I could add a extra bit in to indicate a reset. As we said, I've got my channel element at the beginning, I have my data, and I have about 4 bits in between that aren't being used just because it was easier to do. Right now, this one is built only for effectively plus or minus 21 milliamp signals. If I wanted a 10.2 volt module, it's not going to work. I'm going to have to resize things. I'm going to have to resize my fixed point numbers to allow for both. And I could also optimize utilization just a tiny little bit by getting rid of those wasted bits. So some additional lessons learned. I noted these earlier. Mandatory use of feedback nodes for memory access in single cycle timed loops. LAC on read will cause error at generated immediate files, which is great. You don't waste a lot of time, but the LAC on the write will fail timing during compilation, although per Damien, that will depend upon the particular FPGA that you're compiling for.
Best to assume it will fail.
Best to assume it will fail, yes. Additional resources. I wish this had existed when I started this project. There's a PDF. I keep it on my iPad called the NI LabVIEW High Performance FPGA Developer's Guide. That would have saved me a lot of headaches had it existed when I started this project.
Wait right there. Wait right there. I'm going to write this down.
The version I have on my iPad is version 1.1 from like 3 years ago. I don't know if they've made any updates.
One other thing that you could do on a newer FPGA is use DSPs instead of those high performance, high throughput pluses and plus.
Okay.
That really speeds things up and reduces your fabric.
Okay.
But you have to have DSPs.
Yeah. Well, given that what I still have in my house for my use is the 9074 and 9144 EtherCAT expansion chassis, not going to be playing with DSPs until I have a customer willing to buy me a higher performance unit. So last but not least, this performance has been brought to you by numbers 153 through 159. What that means by that is these are my foster dogs. These are foster dogs number 153 through 159 in the last 5 years. They're all available for adoption because number 160 is coming into the house in the next day or two.
How do you not have 159 dogs?
Well, we have had several fatalities.
Okay.
We also specialize in maternity fostering, so we have the puppies when they're too young for potty training. So it's quite easy to give them up.
I see.
But the little six... I know. the 6 pups turn 5 weeks. They'll turn 5 weeks old starting at 9:46 p.m. tonight with a litter of 5 females and a male. The male, of course, didn't want to ask for directions on the way out and didn't arrive till 5 a.m. tomorrow morning. His sisters were born like 3 hours before him. And then the larger one is a 7-year-old chocolate lab Catahoula mix, and she's available immediately. The puppies are available after their shots next week. They're Lucky Lab Rescue and Georgetown Animal Outreach. And so, any questions or other comments?
I don't know if this is a fixed point, but I guess any thought on using, instead of kind of taking array subsets, on a host we might just use and basically work through the math function, those values get ignored. I know that'll work on single point, but I don't know if on fixed point FPGA it's still. Does anyone know? I know you can. I googled it. You can do it on single point. I don't know if you can do it because normally on a host, like if I wanted to create a dynamic array of things I ignore, I would just stuff it full of NAND. And then I know that the math will ignore that as a number. Yeah.
Oh.
Yeah.
No. You. Okay, no, you get screwed by that.
All right. Good to know.
And it was the same project that taught me that, in that the other people I were working with gave me some code that even though I had some in-range and coerces, I didn't realize in-range and coerce would pass through an NAN.
Yep.
And they had specific faults that they hadn't tested very well that was passing out NANs, which was then being coerced to a floating point before being written down into the FPGA, which was controlling the throttle on my motor, that when they got to the NAN was putting the motor full speed ahead. So throw it, an NAN going into a fixed point, an NAN from a single going into a fixed point is going to go put you effectively plus infinity or the nearest equivalent.
Okay, so yeah, so when it takes the bit pattern, it basically takes the time.
Yeah.
Okay.
Oops.
Invalid inputs equal all on.
Yeah. Well, I thought I was making sure that I had valid data.
Well, the problem with NAN is there are several patterns that it can be.
Yeah.
It's not just one pattern you can test.
Yeah. So you know, I ended up adding a if not a number equals 0, then in range and coerced, or vice versa. I don't remember the order I put it in, but yeah, I had to retrofit a bunch of code for that one. But you know, sub-VI done. Any additional questions, comments?
Yeah, the Boolean array thing Craig mentioned, what I do most times.
Okay.
So yeah, number to Boolean array, and then because then you're working with the raw bit.
Yeah.
You can manipulate that out.
And you can basically bit pack those variables and whatever bit you want.
Okay.
And if you're okay with square, like whole byte size things, then split number join number works really well. But yeah, bitwise, do that.
Go to Boolean arrays, and it's all free anyway, because it's just like literally taking lines and FPGA.
Right. And I had looked at the split and join, but like one place I had to be careful of was here with the multiplication between my actual data and my weighting data, because my weighting data could be between 0 and 1, whereas my actual data could be between 0 and 0.21, or with the particular FXC settings between 0 and 0.25. And so at least right here, and you can see that there is the coercion dot, we do temporarily expand that data to the wider amount before deliberately coercing it back down. Likewise, the accumulator I leave that at the higher resolution there, and I can just keep adding into it.
There is a BI for the IDLs for one of the R-series scopes that has fractional estimation, which is very similar. It has a stream of data in, and it will actually resample it down to the source. It's something that's still way faster than this. We're talking like 250 megasamples down to like 10 megasamples. That's the average.
Yeah.
But if you're going at those speeds, there are actually BIs that do the same concept.
Okay. Yeah, it really wouldn't be necessary in this case because for the particular module, when it's in the high-speed mode, it's still, like 100 milliseconds, 52 milliseconds is what it was. 52 milliseconds in high-speed mode, 832 milliseconds in low-speed mode. But in terms of just saying how useful could this architecture be, one of the calculations is how fast can I put data in and not just start overflowing my buffers. And so that's why I ran those calculations. I'm sure there's other things that can be done to optimize. I don't claim to be an FPGA expert. I'm a lot better at maneuvering through an FPGA than I used to be, but it's not something I do for every project, or really for more than about a tenth of my project.
It seems also like a lot of the stuff you would just put in RT and not worry about it again.
Yeah, unfortunately, again, a mistake I had made on this particular project was the last time I had developed RT was on compact field point systems, and it wasn't fast, and we were a lot more concerned back then. I had a lot more concern because the I/O was also so slow. I was a lot more concerned about memory leaks causing crashes, and so as I started building the individual modules, I was testing them for memory leaks. I wasn't watching CPU utilization as the way I should have been. So first module, great, no memory leaks, was working perfectly. Second module, tested, it's working. Third module, tested, working. And then I turned all of them on at once, and my CPU was trying for 5,000% utilization. Obviously it wasn't succeeding, but there were a bunch of places where I was getting 50 or 60% utilization just for one of my loops. Yeah, which wasn't hard to do.
Yeah.
Realistically, since that was a fixed price project, I probably should have just paid to upgrade the controller myself, go for a more powerful controller, eat the price difference, because I easily spent more time optimizing than the cost difference would have been, even eating it myself. That project had run into some other problems as well, including what turned out to be, a number of LabVIEW bugs that ended up under certain circumstances, which I could never really well reproduce. Just all of a sudden it started validating I had some DVRs, and all of a sudden the handles would be invalidated and throw off all my scaling and my tag engine. And so I had to pull that all out at the last minute and spend the next 2 months post-deployment doing a lot of bug fixes because of that last minute having to pull all this design apart for what turned out to be a low-level bug that Norm Kirchner mentioned to me that I guess someone in NI Shanghai debugged at the assembly level watching the processor execution, that I somehow managed to get into and just said, screw it, I'm totally rewriting this away from what I did, and of course made things even better at the last minute. So I believe Damien is up next.
You want a 5-minute break?
Yeah, we'll take 5 minutes for the changeover.
Thanks, Aaron.
Thank you.
Okay, so I know why we made you wait 3 years.